Hi friends, welcome to my channel. My name is Suryavi. I am currently studying in Sri Venkateshwara College of Engineering of branch Electronics and Communication. Today's subject is about mathematics. In this module, we are going to study about calculations of optimum power in electrical circuits and field theory. Today's topics is about introduction to optimum power, basic concepts of electrical circuits, power in electrical circuits, maximum power transfer theorem, the role of impedance in AC circuits, field theory fundamentals, tools for circuit simulation. Introduction to optimum power. Optimum power refers to the maximum power transfer in the electrical circuits. Understanding the optimum power is a crucial for efficient circuit design. This concept is rooted in the both circuit theory and the field theory. This circuit diagram refers to the Thevenin's theorem of the maximum transfer, where Vs is equals to Vth be this represents Thevenin's equivalent voltage source connected to the circuit, and Rs is equals to Rth. This is the Thevenin's equivalent resistance connected across the circuit. Next, RL be the load resistance connected across the circuit. I be the current flowing in the circuit. VL be the voltage source connected to a resistor. Basic components of electrical circuits. Electrical circuits consisting of components such as resistor, capacitor and inductor. The behavior of these components is governed by the Ohm's law and Kirchhoff's law. This law helps in analyzing the flow of current and the voltage in the circuits. Here is the resistor circuit. According to Ohm's law, V is equals to I into R. According to the resistance, R is equals to V by I. This is the inductor circuit. V is equals to L into di by dt, where V be the voltage between the inductor in volts, where L be the inductor in Henry, where di be the rate of change of current flow in the ampere and dt be the rate of change of time in the seconds. Next, this is the circuit of capacitor, where I is equals to C into dy by dt. Power in electrical circuits. Power in electrical circuit is defined as the rate at which energy is transferred. It is calculated by using a formula P is equals to I into V, where P is the power, I is the current and V be the voltage. Understanding the power helps in determining the efficiency of current. This is the formula for power. P is equals to V square divided by R, or P is equals to I square into R. Maximum power transfer theorem. The maximum power transfer theorem states that the maximum power is transferred when the load resistance equal to the source resistance. This theorem is vital for the designing circuits that require optimal performance. It applies to the both AC and DC circuits. Let us understand the circuit. Vs be the voltage source, Ri be the internal resistance of the source, IL be the current flowing through the load. Next, RL be the load resistance connected across the circuit. Deriving the maximum power conditions. The condition for maximum power can be derived using calculus. By differentiating the power equation and setting it to 0, we find the optimum load resistance. This mathematical approach is essential for understanding the circuit efficiency. The power equations in terms of mathematical form. Derivatives of fractions: 8 divided by x square, 5x plus 3x divided by x square plus 7, x divided by 9, or 7 divided by root x. Load and source resistance. Load resistance is the resistance of the component receiving the power in the circuit. Source resistance is the internal resistance of the power supply. Balancing these resistance is the key to achieving the optimum power transfer. Here, the circuit consists of EMF of battery and internal resistance, load resistance, and voltage load. The role of impedance in AC circuits. In AC circuits, impedance replaces resistance, combining resistance and reactance. The concept of impedance affects both the magnitude and the phase of current and voltage. Accurate impedance matching is necessary for efficient power transfer. Circuit analysis techniques. Circuit analysis techniques such as mesh and the nodal analysis are vital for understanding circuits. These techniques can be applied to find the load and source resistances. Analyzing circuits mathematically helps in optimizing power transfer. Now let us understand about field theory and fundamentals. Field theory explains how electric and magnetic fields interact with the charged particles. It provides a framework for understanding how power is distributed in circuits. Key concepts include electric field intensity, magnetic field strength, and potential difference. Electric fields and potential. Electric fields are generated by charged particles and influence the flow of current. The potential differences across the components determines the power delivered. Understanding the electric fields is essential for calculating optimum power. These are the electric field lines consisting of positive and negative charge. They do not form closed loop and they do not intersect each other. Like charges repel, unlike charges attract. Magnetic field lines and inductance. Magnetic fields influence the behavior of inductive components in circuit. Inductance affects the phase relationship between voltage and current. A true understanding of inductance is a crucial of AC power calculation. This is the magnetic field lines. The magnetic field lines always moves from north pole to south pole and they do not intersect each other and they do not form any closed loop. Now let us understand about inductance. A solid core which is bounded by n number of copper turns of the magnetic flux. After passing the current move towards the coil and produces the magnetic field. Practical applications of optimum power calculation. Optimum power calculations are used in telecommunications, audio system, and power distribution. These applications require precise matching of load and source resistance. Effective power transfer enhance the performance and reliability of electric devices. Tools for circuit simulations. Software tools like SPICE and MATLAB are used to simulate circuit behavior. These tools allows engineers to model circuits and analyze power transfer. Simulation aids in visualizing the effects of varying resistance and impedance. Challenges in optimum power calculation. Variability in components values can complicate optimum power calculations. Environmental factors such as temperature can affect resistance and performance. Designing circuits to maintain optimum power under varied conditions is crucial. Advanced techniques for optimization. Techniques such as feedback control can improve power transfer in complex circuits. Adaptive algorithms can dynamically adjust for optimum performance in real time. Exploring advanced optimization techniques enhance circuit design method. Future trends in power optimization. The rise of renewable energy sources necessitates efficient power transfer methods. Smart grids and IoT devices require advanced power management strategies. Future research will focus on integrated field theory with emerging technologies. Case studies in optimum power transfer. Case studies demonstrate successful implementations of optimum power calculations. Analyzing real-world applications provides insights into best practices. Lessons learned from case studies can guide future circuit designs. Thank you for watching.